Okay, good morning. Today we are going to see about model based control of robot manipulators in this lecture. The outline of this lecture will be as follows. First we have the introduction where we will be discussing quickly about kinematics and dynamics. Kinematics definition, dynamics definition, what is forward and what is inverse kinematics, and what is forward dynamics and what is inverse dynamics. And then we come into the major portion, which is the model based control of robotic systems. Model based implies both kinematic model based scheme and dynamic model based control scheme. And finally, we conclude. Now, coming to the introduction, first we talk about kinematics. What is kinematics? Kinematics is the study of motion without considering the forces associated with. Kinematics can be classified, the robot kinematics can be classified into forward kinematics, which is the input is joint angles, whereas the output is end effector pose, which is nothing but position and orientation. Whereas inverse kinematics it is nothing but the input is end effector pose and the output is joint angle. Now, coming to the dynamics portion, what is dynamics? Dynamics is the study of motion considering the forces associated with that motion. Dynamics can be further classified into inverse dynamics and forward dynamics. What is inverse dynamics? Inverse dynamics, the input is joint trajectories in terms of theta, theta dot and theta double dot, position, velocity and acceleration of the joint angles, and the output is, this is the input is joint trajectory, the output is joint torque. Whereas for the forward dynamics, the input is joint torque and the output is joint trajectories theta, theta dot and theta double dot. The inverse dynamics is useful in controlling the manipulator. Whereas the forward dynamics is useful in simulating the manipulators. Thus, inverse dynamics is meant for control of manipulators and forward dynamics is meant for simulation of manipulators. Thus, we summarize the introduction part in such a way that kinematics is the study of motion without considering the forces associated with that motion, and it has been classified further into forward kinematics and inverse kinematics, where forward kinematics the input is joint angles and the output is the end effector position and orientation, and the inverse kinematics the input is end effector position and orientation and the output is joint angles. Similarly, dynamics is the study of motion considering the forces associated with that motion. It has been further classified into inverse dynamics and forward dynamics, where the inverse dynamics the input is joint trajectories theta, theta dot and theta double dot, and the output is the joint torque tau. And the forward dynamics, it is the input is joint torque and the output is joint trajectories. Forward dynamics is used for simulation of the manipulator, and inverse dynamics is meant or used for controlling the manipulator. Now, coming to the control based on the model of the manipulator. Thus, model based control. First, we discuss about kinematic model based control. It is nothing but closed loop inverse kinematic scheme, because we ensure that the error goes to 0 as the time tends to infinity by a first order dynamic equation. So, CLIK closed loop inverse kinematics algorithm is derived in such a way that the control law is given by q dot, which is the generalized coordinate of the joint is given by q, which can take either theta for prismatic joint or d for theta for revolute joint and d for prismatic joint, the joint variables. So, generalized joint coordinate can be represented by the letter q. So, the joint velocity is represented by q dot, and the control law under this CLIK is given by q dot equal to j inverse, which is a function of q, multiplied by x d dot plus k e. So, this takes care of the error that is associated with the Cartesian trajectory, desired trajectory, actual trajectory. In the inverse kinematics, desired trajectory is given in the Cartesian space for the tip of the manipulator, and the actual tip should follow that trajectory by the computation of the joint angles. That computation of joint angles is obtained by this control law, which takes care of this error getting minimized. This discrepancy getting minimized is ensured by this control law. So, the control law, how we can derive this, which states that first order dynamic aerodynamic equation. So, the error is given by the discrepancy between the desired trajectory and the actual trajectory, where the actual trajectory is given by the forward kinematics function of q, that is what is represented as k of q here, which is nothing but the end effector position. So, error is the difference between the desired trajectory and the actual trajectory, and the error dot is the time derivative of the error is E dot equal to x d dot minus x dot. Now, x dot is represented by j Jacobian into theta dot. We know that from this is forward kinematics, the differential kinematics is f x dot equal to j q dot. That is what is put here, and from this we have this q dot given by this control law, also q dot is given by this control law. So, when we equate, q dot is given by j inverse into x d dot plus k e. So, these two equations, equation 1 and say equation 2, both correspond to q dot. So, when we equate this, we will have E dot, which is we will have the x d dot minus x dot plus k e is equal to 0, which is given by E dot plus K E equal to 0. That is what this first order dynamic equation. Now, coming to the block diagram for that CLIK, closed loop inverse kinematics. The closed loop inverse kinematics block diagram is given in such a way that given the desired trajectory of the Cartesian space for the end effector tip, we have xd dot xd that gets into the control gain, the error between the desired trajectory and the actual trajectory, and that is summarized here, so that it is finally q dot is equal to j a pseudo inverse to j inverse this one into xd dot plus k e, and then q is obtained by the numerical integration of the joint velocity, and this portion is nothing but the forward kinematics. Given the joint angle, obtain the actual tip trajectory, that is compared to get the error, and this iteration process continues till we reach the final trajectory. Now, coming to the dynamic model based control scheme. The rigid body dynamics is given by tau equal to m of theta into theta double dot plus v of theta into theta dot plus g of theta. So, this will be like this, v of theta into theta dot multiplied by theta dot plus g of theta, where m of theta is called inertia matrix, which is of size n cross n, where n is the degrees of freedom of the manipulator, and v of theta comma theta dot is given by, it is called as the matrix which involves the centrifugal and Coriolis effects. Centrifugal and Coriolis effects. This is also of size n cross n. The inertia matrix depends on only the joint angle, not the joint velocity, whereas this matrix which covers the centrifugal and Coriolis effects, the one which depends on both joint angle as well as the joint velocity. And finally, g of theta is the gravity vector of size n cross 1. Thus, the left hand side will be n cross 1, which is equal to n cross n multiplied by n cross 1 plus n cross n multiplied by n cross 1 plus n cross 1, eventually gives n cross 1, which is the joint torque vector of size n cross 1. Assuming that our model of friction is a function of joint positions and velocity, we add that term, which is f of theta comma theta dot, to equation 1, so that the model we obtain is will be tau equal to m of theta theta double dot plus v of theta comma theta dot into theta dot plus g of theta plus f of theta comma theta dot. So, the problem of controlling such a complicated system given by say equation 2 can be handled by partition control scheme. So, the partition control scheme can be modeled in such a way that tau equal to alpha tau dash plus beta, where tau is the n cross 1 or 1 cross n cross 1 vector of joint torques, and here we choose from this model, we choose alpha equal to inertia matrix m of theta, and beta is the rest of that dynamic equation, which is v of theta comma theta dot into theta dot plus g of theta plus f of theta comma theta dot. With the servo law, we have the servo law considered, so that the feedback from both velocity of the joint trajectory, also the position of the joint trajectory error is considered in the servo law. So that tau dash is the servo law given by tau dash equal to theta d double dot plus kv e dot plus kp into error, where the error E is given by the discrepancy between the desired joint angle and the actual joint angle. So, using the equations from 2 till 6 or till 5, it is quite easy to show that the closed loop system is characterized by the error equation, second order error equation, which is given by E double dot plus kv E dot plus kp into error is equal to 0. So, this is the second order aerodynamic equation, which assures that as the time tends to infinity, the error tends to 0. Note this, the matrices kv and kp are diagonal. So, for a joint by joint basis, for the joint I, that aerodynamic equation can be written as E I double dot plus kvi E I E dot plus kpi into E is equal to 0, which is equation number 8. Now, coming to the block diagram explaining or schematically representing the dynamic model based control scheme is shown here, where we give the joint trajectories as the input and we are computing the joint torque based on the servo part here, based on the servo law that is given by tau dash. Okay. So, that the servo law is here, which takes care of the actual position of the robotic system, and this is the portion which is the model based portion. So, we have the dynamic model here. When we add this inertia matrix with this rest of this portion, we get the tau, which is basically the dynamic model of the system. Thus, this portion of the block diagram is called model portion, and this portion is called servo portion. Thus, it has been partitioned into servo law and the model based law, because the dynamic model is getting involved here. So, now the input here is the joint trajectories and the output here is the joint torque. This is the control part, and giving the joint torque to the robotic arm, how we get the joint angle, joint velocity, because we need to have the error coming out from the servo law, which will be happening because of the discrepancy between the desired trajectory and the actual trajectory. So, we need to know the actual trajectory. That is done by this portion, which is here the simulation is happening, which is giving the joint torque to the arm, robot arm, we are getting the joint velocity, that is tau equal to say m of theta, theta double dot plus v of theta comma theta dot into theta dot plus g of theta plus f of theta comma theta dot. So, tau we know because we are giving that as the input. So, theta m of theta into theta double dot is equal to tau minus, say the rest of the portion is say x, and theta double dot equal to m of theta inverse tau minus x. So, theta dot will be obtained now by integration of this acceleration. Further, theta, which is joint angle, will be obtained by the integration of joint velocity. So, this is how we obtain the joint actual trajectories from the manipulator given the joint torque. And we have simulated this for a 2-link revolute planar manipulator with this model based control scheme for the given desired joint trajectories of the two joints. So, we have from the control law we have obtained that the joint trajectories desired joint trajectories have been exactly matched by the control scheme involving the dynamic model. So, the figure 1 shows the joint trajectory matching, joint angular trajectory matching, and the figure 2 shows joint velocity trajectory matching, and finally, the figure 3 shows the joint acceleration trajectory matching. And let me explain you what are all the parameters we have used for the 2R planar manipulator dynamics, so that you can also simulate that, where we have taken the inertia matrix m of theta is given by m11 of theta 2, m12 of theta 2, m21 theta 2, and m22, where m11 is given by, which is a function of theta 2 only, not theta 1, which is given by I L1 plus m L1 square plus m L2 into A1 square plus L2 square plus 2 A1 L2 cos theta 2, where I L1 and I L2 are nothing but the moment of inertia relative to the center of mass of links L1 and L2. I repeat, I L1 and I L2 are the moment of inertia relative to the center of mass of the links L1 and L2. M L1 is the mass of link L1 and M L2 is the mass of link L2. A1 is the length of link L1 and A2 is the length of link L2, and L1 L2 are nothing but the distance from the joints, respective joints, joint 1 and 2, to the center of masses of those two links. Now, M12 is equal to M21 equal to I L2 plus M L2 into L2 square plus A1 L2 C2. C2 is nothing but cos of theta 2, and M22 is given by I L2 plus M L2 L2 square. So, the M part, the inertia matrix part is over. Now, coming to the matrix V of theta comma theta dot, which is nothing but the matrix which involves the Coriolis and centrifugal effects, which is given by H into theta 1 dot plus theta 2 dot minus H theta 1 dot 0, where H equal to minus M L2 A1 L2 sin theta 2. Finally, the gravity term G of theta is given by a vector G1 G2 because of size n cross 1 2 cross 1 for the 2-link manipulator, where G1 is given by M L1 plus M L2 into A1 multiplied by G C1 plus M L2 G C12 cos of theta 1 2, and G2 is given by M L2 into L2 G C12, where G is nothing but gravity acceleration, and in the planar manipulator, which is x and y, the vector G is taken by 0 minus G 0 Why? Because now this is the gravity direction, which is the minus y. That is why we put 0 for x, 0 for z, and for y it is minus of g term, that is all. So, with these values of the matrix and the gravity term, I could able to simulate that to get this trajectory. So, that you can also try with this block diagram. So, that given the desired trajectory, you can obtain the control law, which is given by tau dash, which is basically the combination of the servo law and the model based law. So, that we can able to obtain the joint torque tau. Then we simulate the system by this methodology to get the actual joint trajectories. Now, coming to the concept with the disturbance, the same concept with the disturbance. What happens with the disturbance? When we include disturbance tau d as one of the inputs here along with the system input joint trajectories, we will have with the same scheme, we will have the disturbance getting compensated in such a way that the disturbance can, in our case we have used that as a constant almost in the beginning of the trajectories, and that is getting compressed, so that the trajectory is maintained in order to track the given desired trajectory. This is the scheme we have used by including the constant disturbance, a constant value disturbance for a while, and then we have obtained the desired trajectory matching with the actual trajectory perfectly, as can be observed in the plot. Then we come to Cartesian model based control scheme. So far we have seen joint space model based control scheme, and this is what Cartesian model based control scheme. So, the rigid body dynamics can be written as F equal to mx of theta into x double dot plus Vx of theta comma theta dot into theta dot plus Gx of theta, with the joint torque computation or the control law here is tau equal to J transpose F, Jacobian transpose multiplied by the force. So, the block diagram associated with that Cartesian model based control scheme is given here, where we give the end effector trajectories, the tip trajectories in terms of position, velocity and acceleration. We could able to obtain the joint torque or the control law, which is J transpose multiplied by F, where F is the summation of m x of theta plus V x of theta comma theta dot into theta dot plus G x of theta. In the same way, simulation is done with the dynamic model, and from the joint angle obtained from the simulation, we could able to do the forward kinematics and differential kinematics to obtain the actual position and the actual velocity of the end effector tip. That has been fed back through the servo law in order to obtain the actual, in order to obtain the error, so that we could able to compute the joint torque through J transpose F. With this control law, we could be able to get the actual joint torque, and from that we could be able to obtain the joint angle through forward kinematics and inverse kinematics. We could be able to forward kinematics and differential kinematics, we could be able to get the position and velocity of the manipulator. And similarly, for the 2 or planar manipulator case, we could able to obtain the desired trajectories. This is basically end effector position, which is in centimeter, and this is also the joint angle trajectory. This is correct. This joint angle trajectories. Now coming to the final conclusion part. So, we just finished with this Cartesian based control, and now we conclude this session in such a way that in this lecture we have simulated both the kinematic model based control scheme and the dynamic based control scheme. We have in this lecture we have seen the basic definitions of kinematics, dynamics and the types of kinematics, the classification of kinematics and the classification of dynamics in this lecture, and then we entered into the model based control scheme which is further classified into kinematics model based control scheme and dynamics model based control scheme. In the kinematics model based control scheme, we have seen the CLIK, that is closed loop inverse kinematics, showing the aerodynamic equation, which is the first order aerodynamic equation, whereas for the dynamics based control scheme we have seen the inverse dynamics based control scheme, which is the dynamic model based control scheme, which is involving partition control scheme, and also we have done that through joint space control and Cartesian space control. Thus, in this lecture we have seen the control scheme of manipulators based on the model based control. The model based control has been classified into kinematics model based control scheme and dynamics model based control scheme. The kinematics model based control scheme, what we have seen in our lecture is closed loop inverse kinematics, that is called CLIK, click control scheme, where we have proved that through the first order aerodynamic equation, which assures that the error converges to 0 as the time tends to infinity. Then in the dynamics model based control scheme, we have seen partition control scheme involving both joint space control scheme as well as the Cartesian space control scheme. And in the beginning of the lecture we have briefed the definition of kinematics and dynamics and also the classification, that is the further broad classification of kinematics, which is inverse dynamics and inverse kinematics and forward kinematics, and the classification of dynamics, which is inverse dynamics and forward dynamics. Thank you so much.